Unit 1 of Grade 2 Mathematics, the Bell series. Before we're coming to sequences, it's better to revise sets and functions. I think everyone knows something about set and function. Now set, any well-defined collection of objects. For example, it's not well defined because the word beautiful is dependent. On the other hand, the set of natural numbers less than 1000, it is a set. That's why, because natural numbers are really well defined, especially the numbers from 1 up to 1000 are really well defined, and therefore it is a set. In case of function, a relation such that no two ordered pairs have the same first coordinate and different second coordinate. For example, consider the following arrow diagrams. In the first diagram, if you can see, 1 maps to A, 3 maps to B, and 5 maps to B. Both 3 and 5 are maps to a single object B. In this case, it satisfies the definition and therefore it is a function. In the second case, the numbers 1 and 5, I mean 1 and 3, are mapped to two numbers. 1 maps to 4 and 5, 3 maps to 6 and 7. It's somewhat not logical, and therefore it is not a function. On the other hand, 1 maps to 3, 5 maps to A, and 3 maps to B. Such function is a one-to-one function. In case of sequences, find what sequence is first. A sequence is a function whose domain is a set of positive integers or a subset of consecutive positive integers starting with 1, and the functional values a1, a2, a3 up to an are called the terms of the sequence, and an is called the general term or the nth term of the sequence. The sequence a1, a2, a3, and an up to infinity is also denoted by the set containing an or the set containing an for n runs from 1 up to n. Sequences can be described by 4 ways. The first is listing the terms of the sequence. For example, the sequence or the set containing 1 over 2, 1 over 3, it continues 1 over n and continue. In this example, the terms are listed. Some of the terms are listed as you see, and this way of description is called listing the terms. Second one, writing the general term. From the above example, the listed terms are generalized with a formula 1 over n. and this is called writing the general term of the sequence. And the third one, drawing graphs. It's possible to draw the graph of each function. Sequence a function, and we can draw the graph of this. Therefore, drawing the graph of a sequence is a way of description. And the last one, using recurrence relation. Using recurrence relations, what is recursion formula? The formula that relates the general term n of a sequence to one or more of the terms that came before is called a recursion formula. A sequence that is specified by giving the first few terms together with a recursion formula is said to be defined recursively. The values of recursively defined functions are calculated by the repeated application of the function to its own values. For example, the Fibonacci sequence Fn is defined recursively by the conditions f1 is 1, f2 is also 1, fn is given by fn minus 1 plus for if the n greater than or equal to 3. In this case, each term is sequence described by its first few terms is given by 1, that means f1 1, f2 1, f3 2, that means 1 plus 1 2, f4 that is 1 plus 2 that is 3, and the next term 2 plus 3 5, 3 plus 5 8, and so on. Such sequences are defined recursively. A sequence that has a last term is called finite sequence, whereas a sequence that does not have a last term is called an infinite sequence. The domain of finite sequence is a finite natural number. The domain of an infinite sequence is natural number, the whole natural number. For example, 1, 2, 3, and up to 10 is a finite sequence. That means one can count all the terms of the sequence. In the second case, 1, 2, 3, it continues up to infinity. Is an infinite sequence. No one can count all the elements of the sequence here. Some sequences do not have a simple defining formula. For example, if we take n is equals to n cubed plus n squared over 4 minus 3n over 4, the first few terms are n is equals to 1 over 2, 15 over 2, 27, 65, and it continues. It is somewhat difficult to predict the formula from the listed terms, and therefore it is better to say some sequences do not have a simple defining formula. Let's see some exercises. Exercise 1. List the first 5 terms of each of the sequences whose general terms are given below, where n is a positive integer. N is given by 3 into 1 minus 1 the power of n over 1 over n. B, n is equals to cosine of n pi over 2. C, n is equals to the nth term, the nth prime number. That's it. Then the second question, find a formula for the general term an of each of the following sequences, assuming that the pattern of the first few given terms continues. Let's see the answer of the questions. The first case, the sequence given by its general term an is equals to 3 into minus 1 the power of n over n can be listed just like this. When n is 1, 3 into minus 1 the power of 1 over 1 is just minus 3. When n is 2, it is 3 over 2. When n is 3, it is minus 1. Where n is 4, it is 3 over 4, and it continues. These are the sum of the terms. In case of B, an is equals to cos n pi over 2 is the general term, and we can list some of the terms. When n is 1, cosine of pi over 2 is 0. When n is 2, cosine of pi is minus 1. When n is 3, cosine of 3 pi over 2 is 0, and it continues just like this. And the third one, an is equals to the nth prime number. Natural numbers can be divided into as prime numbers and composite numbers. Prime numbers are starting from 2. That means prime numbers are numbers which are divisible only by themselves and 1. And therefore the first prime number is 2, the next 3, 5, 7, 11, 13, and it continues just like this. The second question, the first few terms are listed, and we have to find the general term. An is equals to 3, 6, 9, 12, 15, and it continues. All the terms are a multiple of 3, and we can generalize this as 3n. An is equals to 3n. When n is 1, 3, 2, 6. Where n is 3, it's 9, and it continues. Therefore, the general term for the listed terms is just 3n. In the second case, n is equals to 2, 7, 12, 13, and it continues. We have to find the relationship between the terms. For these terms, 5n minus 3 can fit for all terms. On the other hand, an is equals to 0, 2, 0, 2, 0, 2. It continues just like this. The general term for this sequence is 0 if n is odd, but 2 if n is even. That means a1, a3, a5 is 0, a2, a4, a6 is just 2, and it can be generalized as an is equals to 0 if n is odd, 2 if n is even. For the next lecture, we will discuss about arithmetic sequence and geometric sequences. If you like this video, please subscribe, share, and like. Thank you very much.